This is the Mechanics Homework Booklet, question 33. A car of mass 970 kilograms is travelling at 15 metres per second along a level road when its driver performs an emergency stop. The car's braking system applies a constant braking force of 6.1 times 10 to the 3 newtons to the car. You are told to assume that the braking force is the resultant force acting on the car. This means you can ignore any other effects like air resistance. So first of all, calculate the change of momentum of the car during the emergency stop. Clearly the final velocity and final momentum will be zero. So the change in momentum will be 0 minus the initial momentum. So here we have the mass multiplied by the initial velocity, giving us a momentum of 14,550 kilogram meters per second. It's appropriate to give this answer to two significant figures using standard form as shown. There is no need to record the negative sign in this final answer for 1 mark. Next, you're asked to calculate the distance the car moves in coming to a halt during the emergency stop. Since we know the braking force is the resultant force and we can ignore air resistance, we can assume that the acceleration is constant. For this reason, it's appropriate to use the equations of motion. So you can prepare a SUVAT list. S, the displacement, is what we want to know. We have an initial velocity of 15 meters per second, a final velocity of 0, an unknown acceleration, and unknown time. This is too many unknowns to proceed to find the displacement S. So we need to look for an alternative way to find one extra piece of data, the time. So looking back to the question and the information given, we are told the force that acts upon the car. We also know the mass of the car, and using the initial velocity we can find the initial momentum. So we can use impulse, force times time, equals change in momentum. Rearranging to find the time, during the braking we have change in momentum divided by the force. Substitution then, using our change in momentum from the previous part of the question, bringing that down to the top line of our fraction, and then the force, the braking force acting upon the car below. Notice I've used all the significant figures that I could, having kept a record of those in part 1. This gives a value for time, which now completes our SUVAT list, enabling us to find S. So we can use the equation S equals a half U plus VT. A half times the initial velocity, the final was 0, and then multiplied by the time. This leads us to an answer of 17.9 metres. Finally, we are now told that the car is loaded with passengers and luggage. Again, it travels at 15 metres per second. You are required to state and explain how this loading of the car affects the braking distance. And you can assume that the braking force remains the same. Notice there are 3 marks allocated to this answer. The first thing you need to do is state the effect. So here we have that the braking distance increases. This is a method mark, but no mark was actually allocated to it. So it's a requirement for you to be able to proceed to the later 3 marks here. So if you were to say that the braking distance decreases, you could gain no more marks. So the marking points are that loading with passengers and luggage increases the mass. Looking back at your previous solution to part 2 above, you can realise that a greater mass leads to a greater initial momentum, and if you look at the maths in your equation there, that would lead to a greater time in order to bring the car to a stop. A greater time to bring it to stop would result in a greater distance travelled whilst braking. Notice how I've been using the maths logic from the part of the question above. Whenever you're unsure how to proceed in a question, it's often well worth looking at the previous answer and considering whether you may use that in some way. Here I have presented one way in which to answer the question, though the mark scheme did allow for 2 alternative ways of presenting the physics. Both of these alternatives began with a statement that the braking distance increases, and the first point that there would be an increase in mass. However, the increase in mass could be linked to a greater kinetic energy or more work needing to be done to bring the car to a halt. If more work was done by the same force, that would mean a greater distance travelled. This could be backed up with the equation work done equals force times distance. The final approach had a look using the concept of acceleration. So an increase in mass would lead to smaller acceleration, and smaller acceleration for the same change in velocity would again mean a greater distance. Again, this could be illustrated with one of the equations of motion.